You deploy a new AI agent into a real-world workflow. You use the most capable model available and iterate on the prompt hundreds of times. But once it goes live, it acts brilliant 1 minute and hallucinates the next. It drops tasks, it gets confused. Your success rate stalls out under 70%. When this happens, the common reaction is to blame the model's intelligence. We assume the logic is flawed or the prompt wasn't specific enough. But the failure often isn't in the model's ability to think, it's in the system's ability to execute. We are taking long-chain, multi-step tasks and treating them like simple chatbot conversations. Engineers now define the agent as two parts, the core model and the harness. In this evolution, prompt engineering is a point, context engineering is a line, harness engineering is a 3D box, the complete system managing how the model behaves. A model without a harness is like a wild horse without reins. It has the raw capacity for power, but no reliable way to sustain action or recover from mistakes. The harness acts as a set of guiding reins built to catch the AI when it inevitably drifts off track. To make this system reliable, you need 6 specific operational layers. Layer 1 is boundaries and organization. You define strict roles and curate exactly what the model is allowed to see. If you flood a model with irrelevant data, it loses focus and begins to ignore its core instructions. Layer 2 is the tool system. Rather than giving a model open access to your environment, the harness dictates exactly when a tool should be used, and then it filters the raw results before passing them back to the model. Layer 3 is orchestration. The harness forces the model onto a rigid track: plan, execute, and evaluate. Layer 4 manages memory and state. The harness separates past actions and intermediate results from future goals, preventing amnesia during complex tasks. Layer 5 is evaluation. An AI cannot effectively grade its own work. The harness provides an independent mechanism to verify if an action actually achieved the intended result. Finally, Layer 6 is constraint and recovery. When an API times out or a model misinterprets a step, the harness catches the error and rolls the system back to a stable state to try a different path. These 6 layers transform a text predictor into a reliable worker, capable of navigating a digital environment without constant human oversight. Anthropic saw the need for this architecture when they identified a problem called context anxiety. As a task runs long and the memory window fills up, the model begins to rush and drop crucial details to save space. Instead of compressing data, Context Reflect extracts vital conclusions from a full model and passes them to a fresh agent, a clean reboot. They also separate the code-generating worker from an independent evaluator that physically tests the interface to ensure it works. OpenAI uses a similar strategy to prevent information overload. Instead of giving an agent a massive manual of rules, they provide a dynamic index. The agent only loads the specific instructions it needs for the current subtask. They also utilize isolated sandboxes. Their agents run code in closed environments where they can read their own logs, identify bugs, and correct themselves without needing a human to intervene. By focusing on these scaffolds, labs like OpenAI and Anthropic have reached a point where AI writes and tests millions of lines of code. Success isn't coming from a massive leap in model intelligence, it's coming from building better environments for the models we already have. This transition changes the nature of human labor. In a world of autonomous agents, we are no longer required to write every line of logic or spend weeks perfecting a single prompt. The role of the developer is evolving. Success now depends on your ability to act as an environment designer. This leads to a new rule for troubleshooting. When an AI agent fails or gets stuck in an infinite loop, the solution is rarely to tell the AI to try harder. Instead, you must audit the system and identify exactly what structural capability is missing from the harness. Mastering the harness is the dividing line. It separates those who run fragile experiments from those who build robust products that actually work.